Okay, today will be the first of 3 videos covering Chapter 12, which is on electronic properties. And we've covered some really fascinating things this semester about how material science leads to exciting new innovations. I think that possibly the most interesting and exciting of the different aspects of material science is electronic properties. It's what makes possible so many of the interesting things that are really on the cutting edge of what materials can do. What we're going to cover is in generally 3 areas. In this video, we're going to cover electrical transport. In the second video, we'll talk about dielectric materials largely. And in the third video, we're going to spend time talking about piezoelectric materials. So to start with, what are materials that can conduct electricity? How is electricity transported through material? Well, it, like any other transport process, just like heat or mass, relies on a simple relationship. The relationship is that if you have a flux, then you have to have a driving force, and you have to have a constant of proportionality. So if it's diffusion, so this is mass transport, we call that Fick's first law. And we said that the diffusion flux, J, is going to be proportional to the concentration gradient, dC dx, times negative diffusion coefficient. So that's our constant of proportionality. If it's heat transport, we call this Fourier's law, or also Fick's first law, but for heat. So now JQ, the flux of heat, is going to be proportional to the temperature gradient, and then the thermal conductivity is the coefficient right in front of it, or the constant. So we have a different scenario for electrical conductivity that we need to derive. We know probably from high school chemistry or high school physics, you probably have seen this relationship that V equals IR, meaning the voltage is equal to the current times the total resistance. Well, starting with this, we can eventually get this to look something like a flux and a driving force. So first off, what is the flux? Well, it's certainly going to be the current. Current has units of amps per meter squared, and if we simply remember that 1 ampere is a coulomb per second, and that a coulomb is just a number of electrons, all of a sudden we realize that current is number of electrons per meter squared per second, so that's a flux. So that fits. So what is our driving force? The driving force is going to be the electric field. The electric field is the difference in voltage divided by the difference in distance. So it's the potential difference divided by the physical separation, right? That's our electric field. Therefore, we now only need the constant of proportionality. The constant of proportionality for flux of electrons moving through material in response to an electric field is called the electrical conductivity. Written with the Greek letter sigma, it has units of Siemens per meter, which is equivalent to inverse ohms, or 1 over ohms, multiplied by 1 over meters, or sometimes mho over meter. These all have the same exact meaning. Okay? So now we can almost make this start to look something like V equals IR. We're getting closer. If we recognize that I is our current and V over R is the voltage divided by the total resistance, the first thing we realize is that we have to change from resistance, which is not a material's property, but rather depends on material properties as well as the sample geometry, into something that is just the material's properties, which is electrical resistivity, right? So this is the material's property. This does not depend on how big or small the sample is, it just is. Silicon carbide has an electrical resistivity. Copper metal has an electrical resistivity. It doesn't depend on the size of the sample, right? This we use the Greek letter rho, and it has the units of ohm times meter, or ohm meter, right? So therefore we know immediately that electrical conductivity is equal to just 1 over electrical resistivity, and vice versa. Now in Ohm's Law we do not use electrical resistivity. Instead we use total resistance, and these are not the same thing. Rho does not equal big R. They're related by the geometry of the sample. So if we take a sample like this, where we have some length of sample that we're passing the current through, it has some cross-sectional area A, then we can decide that the electrical resistivity, rho, equals the total resistance of the sample multiplied by the cross-sectional area divided by the length. Or in other words, if we wanted to make a resistor that has some arbitrary total resistance, all we need to do is use a material where we know the resistivity, and then we can design the cross-sectional area and the length to whatever suits us for our design to have the exact resistance of interest. Right? Now, if you have a larger cross-sectional area, you're going to accommodate more current through that sample, or more easily anyways, than one that has a smaller cross-sectional area. And actually, this is actually a pretty good explanation of something that we observed this semester. Earlier on this semester, when I did the iron wire demo, you'll remember that for that example, I needed to apply electricity in an AC current back and forth through my wire until it heated up. So I was relying on something called Joule heating. Joule heating is the process of heating something by passing a current through it. And we can write it that it's proportional to I squared R times T. So it's proportional to the current times the total resistance times time. Now when I first did this demo, I knew that I couldn't wait all day for this wire to heat up to 912 degrees Celsius, so I needed it to be done in a short period of time, something like 5 minutes. And I also knew that if I picked a wire that was too weak, that would break. So my first estimate for using a wire, I picked 12 gauge wire. 12 gauge wire is pretty thick. As you go up in number of gauge, the wires get smaller and smaller. So I started out with 12 gauge wire. And when I did this, I soon found out that I wasn't able to reach 912 degrees Celsius because as it was heating up, it was taking a lot of current to heat it up because the cross-sectional area was so big that my resistance was low right here. In fact, I blew a circuit in my lab because I went over the maximum current, which was a 30 amp fuse inside my circuit breaker. So then I wised up and I went and I used a smaller wire, an 18 gauge wire, which is down here. That allowed me to heat it up much more rapidly. The Joule heating was much larger because we've increased our resistance by going to a smaller cross-sectional area. And that made it possible to do this demo. So let's do an example of this type of calculation. How much heat would we generate by passing 15 amps if we had a long rectangular sample, and we know the dimensions, and we're going to run it for 1 minute? If we assume that we have a copper sample, and that we know what the electrical resistivity of that copper is, can we calculate how much heat this thing generates? So to do that, we remember our new formula. We say rho equals big R times A divided by L, right? So then if we know our sample, it looks something like this, where this is 10, this is 4, this is 3, then we can say that the heat, we're going to estimate that the total heat generated is going to be equal to the current squared, I squared, times R, the total resistance, times the time that we hold this current for. And you can see that this should have the units of heat. This should come out in joules, but we can double check that. We know that an ampere, so we start out with A squared, ampere squared. We're going to multiply that by ohms times seconds. And then we just need to remember that an ohm, right here, is equal to a joule per second per amp squared. So we've got A squared, then this is going to be times joule per second, A squared times second. Everything cancels out except for joule. So it should give us energy, or heat. So when we punch the numbers in, we get 15 amp, this whole thing squared, multiplied by rho times L over A, multiplied by 60 seconds. Plugging in further, we find that this is equal to 15 amps squared. 15 amps squared times 16.78 times 10 to the negative 9 ohms times 10 to the negative 9, oops, running out of space here, times 10 to the negative 9 ohm, let's see, that's ohms per meter. We're going to multiply this by the length, 0.01 meters, divided by 1.2 times 10 to the negative 5th meter squared. Okay? Multiply this by 60 seconds, and we finally come to 0.188 joules or 188 millijoules. So we've accurately calculated how much energy passing this wire through, this current through the wire should generate via joule heating. Now, if we have copper wire and we know its original temperature was 25 degrees Celsius, we could then ask what will the final temperature be if we know what the specific heat and the density of the copper wire is. To do this one, we're going to have to recognize that by the definition, specific heat is equal to Q, the amount of heat that we need to put into the system in order to raise some quantity, say a mass, some change in temperature, right? So therefore, we're going to say that 3860 joules per kilogram Kelvin must be equal to the amount of heat that we're putting into it. In our case, that's 0.188 joules divided by, we need to know the mass, and we're not given the mass, but we do know the volume, and we're given the density, so we can say 8.933 grams per centimeter cubed. We need to multiply this by the volume of our sample in cubic centimeters, and then we're going to multiply that by delta T. So what's the volume? Volume is just going to be 10 times 3 times 4 millimeters cubed, which if we punch in and do the math, we find that's equal to 0.12 centimeters cubed. Therefore, our centimeter cubes are going to cancel when we plug that in, and we find that the amount of heat that we generate, solving for delta T, will be 0.045 degrees. Therefore, our temperature final will be equal to 25 plus that number will be 25.054 degrees Celsius, which means our wire does not really heat up that much. This is using at, let's see, this was at 15 amps for 1 minute. The circuit breakers in your home are rated to about 20 amps, and you might use them for much longer than 1 minute, but you see how much we're actually heating copper up. It's not very much. If you're using normal wires and nothing crazy, then you should not run the risk of heating up too much to be dangerous, right? So we could do the same thing with silver bar with same dimensions. We would need to know what the specific heat of that sample was. We'd need to know what the density and the resistivity of silver was, and we'd find that it's going to be a different value. Now, sometimes metals are not meant to be very electrically conducting. Rather, they're meant to be very resistive, right? Nichrome, for example, has a very high electrical resistivity. So if we took and we calculated the amount of heat increase for this sample, for the same size of sample, we'd find that it's very, very large. Nichrome is the same metal that's used in your heating element on your furnaces, in your stoves in your house. If you don't have gas stove and you have a range top that's electric, it actually probably has something like nichrome there, which intentionally has a high resistivity, therefore it has a large resistance, therefore the amount of joule heating is very high for the amount of current that you put into it, meaning it can cook your food just by heating up electrically. So electrical conductivity, or electrical resistivity, the one over that value, is a fascinating material property. To my knowledge, it's the one that spans the largest range of values as you look at all different classes of materials. One way to see that is in a so-called Ashby plot. In this Ashby plot shown here, on the y-axis we show electrical resistivity. At the top we have very good insulators. Down at the bottom we have very good conductors, and then moving along the x-axis it can be whatever. In this case it's cost. But you can see we go from 10 to the negative 9 all the way up to 10 to the positive 15. People have reported there's something like 28 orders of magnitude difference in these materials in terms of electrical conductivity. So huge, huge range in values. And we're going to try and understand by the end of class today why or where this is coming from, why we should expect to see such large changes, right? Some general rules of thumb: you might expect a metal to have an electrical resistivity somewhere or conductivity on the order of 10 to the 7th. Semiconductors, a class of materials we're going to describe soon, should be 10 to the negative 6th up to 10 to the 4th. And insulators, another class we'll describe soon, something like 10 to the negative 10 or 10 to the negative 20, so very insulating, right? Now, let's note, we can move charge through a material. We can have electrical transport by either moving electrons, by moving holes. Holes are simply the absence of an electron, and we'll describe that better in just a moment. Or you can even have ions moving through the lattice, as we described in a previous chapter. So let's consider electronic transport first. And to do that, we really need to introduce or reintroduce the concept of bands that we talked about in our very first week of class. So we know that not all electrons in a solid are available for conduction, but rather it's the ones that are the valence electrons, the ones that are furthest out. Those are the ones that are going to be involved in electrical transport. The ones deep within inside the material, they're not going to be involved. Now, how do these outermost ones behave? It's going to depend on their local environment. So it depends on environment. What do I mean by environment? I mean how many nearest neighbors, how many other atoms are around it. If it's a single lone atom, we know that we could count the energy levels. They would just start ticking upwards, right? For each electrons that you start to put in orbitals, you can put 2 per orbital, and then you have to go upwards in energy. However, if you put two atoms close to one another, now you can see that this space overlaps a little bit. And we know that electrons of the same energy cannot occupy the same volume of space. This violates Pauli exclusion principle. Therefore, since they can't occupy the same energy level if they are going to occupy the same volume, we must have one energy level that's slightly higher for one set of atoms, and one has to be slightly lower. And now if you've got 3 atoms, you have to have 3 splitting. If you have 4, you have to have 4 splitting. And eventually, if you have a continuous solid made of roughly infinitely, many atoms, essentially, you now, instead of having 1 or 2 energy levels, you form what's called an energy band. This band is going to fill some energy continuum, right? And it's going to have very, 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 very closely spaced energy levels. We're going to call them, for now, infinitely closely spaced levels. There's still some finite number of electrons you can put in there, but there's basically no difference in energy between these, okay? Now, one other way to see this is if you were to plot atomic separation. So these are 2 atoms, and you have them separated by some distance a. As you have them very far apart, they look just like we'd expect them to. We've got orbitals that just go upwards, right? It would just look like normal. If you bring these closer together, that forms these bands, and more importantly, a new concept, which we're going to describe right now, it forms a band gap, right? So it forms not only a band, which we just described, it also gives rise to a band gap. And we will not be describing why a band gap forms in this class. You'll have to take it for granted, and there's other courses you can take that describe that a little bit better. But for now, we're going to say that a band gap is a region of energy, for example, between EV right here and EC up here, where it is disallowed. No electrons are allowed. No electron occupancy allowed. That's going to have important implications soon. So, in fact, once we have the notion that there's bands that exist in a material, that alone can explain why we have metals, which are extremely good conductors, and we have insulators, which are terrible conductors. Here's the concept. First off, if it's a metal, whatever the material is, metal or an insulator, whatever it is, it has some finite number of electrons. We know we could count them up in the material. Now, if the material was at absolute 0, those electrons are going to occupy the lowest energy levels that are available to them. And then as you heat this material up, you're going to be able to have them start to occupy higher and higher energy levels. So let's consider absolute 0 at first. They're going to take the lowest space. If you fill up the spaces available, and where they stop is right in the middle of a band, let's say that that's this line right here, that's where they stop filling, if this was absolute 0. That happens right in the middle of a band. That means this is a conductor, because if you do something to try and move these electrons around, there's empty seats, right? This is filled, this is empty. So there's empty seats on which they can move around. So whether if that happens in the middle of a band or at the place where 2 bands overlap, you get conduction. That looks like a metal. However, if that level lies in the middle of a band gap, and it's a small band gap, we call this a semiconductor. If that happens in the middle of a large band gap, we call it an insulator, right? And this has important implications. Basically, I think the easiest way to think of this is like a bus. If we were to draw a bus, a really dorky cartoon of a double-decker bus in England, right? Double-decker buses have 2 floors, right? So let's say you've got seats on the bottom floor, and you're full of electrons here. Totally full up. You've got 2 per seat, up and down filled, nowhere else to put electrons. But you do have a stairwell, and you can, if you want to spend the energy, you can go up in energy. So an electron down here, this electron right here, he's not able to move around the bus because it's completely filled. Can't move, no seats. Right? If he wants to move, he can't, because those seats are all filled. But if he pays the energy to get promoted, all of a sudden now he goes upstairs where there's lots of empty seats. None of these states are occupied by electrons. So now if our electron does arrive up here, it can move very easily. Conduction possible because empty seats available. Okay, so this concept, which I'm describing right now, that you have to overcome the energy of the band gap if you want to be a conductor, gives rise to this radical difference in electrical properties. And so let's introduce some two terms here. We're going to call this band right here the conduction band. Conduction band. And we're going to call this band right here the valence band. Okay? We've already talked about the Fermi level. The Fermi level is just whatever energy it takes. If you were at absolute zero and you were filling up your electrons, and wherever that goes to. If it happens to completely fill a band, then you're going to have either a semiconductor or an insulator, depending on the size of the band gap. If that level fits in the middle of a band, great, you've got a metal. Okay? So a metal, you can think of it in this bus analogy. Sure, there's a row of empty seats up here, but a metal has empty seats down here as well. So the electrons can move around pretty easily. Okay? So valence band, conduction band, you can read about those in the book a little bit more. There's lots of ways that people go about drawing these things. Basically, here would be the Fermi level. That's where, if it was absolute zero, this would be completely filled, and then this would be completely empty right here. Obviously, we're going to introduce a concept that it doesn't have to be completely filled below and completely empty above, but rather, if you have some thermal energy, you can have some of these empty because some of those electrons have moved up a little bit. So let's describe that right now. First off, let's remind you what a hole is. If we used to have an electron here and we kick the electron out, we have a hole left over. So the hole is plus charged, whereas the electron is negative charged. And think of it as the absence of an electron. And we will come back to that when we talk about semiconductors. Okay? So let's remind you this idea that I've just said, that you have some probability of electron occupancy as a function of energy. So what you see in this plot, we have probability of occupancy. We can never have more than a probability of 1. That's 100%, right? But here, as we increase energy, as you go up in energy, if we were at absolute 0 Kelvin, then you would completely fill this area. That's this black line, meaning 100% of your electrons would be right here if 0 Kelvin, right? But we're not at 0 Kelvin. Maybe you're at a slightly higher temperature. Well, that changes things. That means instead of having that place completely filled by electrons, you might have this. So now in red, it's going to look like this red line here, which does this. So now some of your electrons have moved over, right? You had electrons move here, and now they're at a slightly higher energy level. And if you go to even higher energy levels, it's going to be even more drastic, right? Now you've got something like this curve. So the higher and the higher your temperature, you're taking the electrons that were here and you're putting them here. They've moved, right? So the higher your temperature, the more likely that you have electrons occupying these higher energy levels. It's not like it's 100% occupancy. You have some small occupancy, okay? This is how semiconductors start to become conductors. At 0 Kelvin, this is completely filled. But if you're above 0 Kelvin, now you start to have a it's not just a flat line for your distribution of electrons. You're going to have some electrons here, and you're going to have some missing electrons here, some missing electrons. And another way of saying that is just that you have holes, H+, right? And at a higher temperature, you have even more holes and electrons, okay? At the higher temperatures, it gets even a larger amounts. So another question is, how else? Clearly, temperature is one way to promote carriers from the valence band up to the conduction band to make a semiconductor more electrically conductive. How else might we do it? There's a number of ways. One really important one that we're going to talk about later in this chapter is light. Where basically, if you have a conduction band and a valence band, here's our valence band, and here's our conduction band, and we introduce a photon of light with sufficient energy, it might hit an electron here and promote it up to here, creating a hole here and an electron there. This is the fundamental operating principle behind solar cells, photovoltaic devices. You introduce a photon of light, and as long as its energy is at least as large as the band gap, then it can promote an electron over the band gap, and you can now have both an electron and a hole, and if those don't recombine immediately, we can do interesting things with them, like create solar cells. We'll talk about more of that in next chapter, or in next video. So this would be a good question at this point to check our knowledge. We've just said an insulator and a semiconductor, both, if they're both at the same temperature, they both have band gaps, should they have the same electrical conductivity? Why or why not? A good way to answer this question is to recognize that a semiconductor has a small band gap. We'll call that E sub G, whereas an insulator has a large band gap, you'll remember. EG is much larger. Therefore, the amount of holes which are created here by promoting electrons up to here might be quite large. But in our insulator, you might only get a relatively small number, right? Because there's a bigger energy difference. Therefore, if you have the same temperature, you're going to get a much higher conductivity in your semiconductor than your insulator because you promote fewer carriers. Okay? Another alternate explanation can be thought of in terms of bonding. Insulators tend to be ionic or strongly bonded, and so the electrons are held much more tightly. But in semiconductors, they're weaker bonds, so the electrons aren't held quite as tightly, so it's easier to strip away an electron to create a free electron and leave in its place the missing electron, which we call a hole. Okay? So let's talk about electron mobility before we move on. Electron mobility, the reason we need to introduce this is to answer a puzzling question. The question is as follows. If we have an electric field, we know from physics 2, or even physics 1, you know that if you have an electric field pointing this way, and you have a charged particle like an electron, right, an electron, it gets moved that way. Or if you have a charged particle that's positive, like a hole, it would get moved this way. So let's say we have a large sample. We have a 1 foot long piece of copper. If I put a battery voltage across either end of that, what conductivity should I read? It's going to be a finite value. So that's sort of a paradox, because if the electric field is uniform, it's not changing across that entire sample. Shouldn't the charge carriers, be they electrons, holes, or ion, just continue to accelerate continuously all the way across this material? And if they're accelerating continuously all the way across it, shouldn't the conductivity approach infinity if I had a big enough sample that I put the electric field across? Obviously they do not. Voltage is finite, and so that's not the case. So what's the reason for this? The reason that we can introduce to best explain this is the concept of drift velocity. Drift velocity comes about because just like if you jumped out of an airplane, if we had, you know, the Earth down here, and you are up here, and you're falling towards the Earth, you experience the pull of gravity, the acceleration of gravity. Gravity, acceleration. So as you're falling, you might think that you're going to continue gaining speed since you're continuously in the field of gravitational acceleration, but we don't, because sooner or later we're going so fast that we have a forced balance. We say that the air that we're colliding against slows us down, right? It's causing us to decelerate at the same rate that gravity is accelerating us. So we have no net change in velocity. Instead, we reach terminal velocity. Terminal velocity. So that's exactly what we see. If we measure a resistor, we don't see infinite conductivity. We see some finite conductivity. So our electrons or our holes or whatever, they must be reaching terminal velocity. So there's no air that they're encountering. What are they encountering? They must be encountering something that we're going to call something akin to frictional forces. And what would those be? Those are going to be scattering events, meaning the electron is moving through the material, but it's bouncing into things. It's going to bounce off of imperfections, impurity atoms, dislocations, grain boundaries, vacancies, interstitials, thermal vibrations, all of the above. All of those things can cause a carrier, be it a hole or an electron or an ion, to become scattered. And that means it's going to slow it down as it moves through the material. And we can see evidence of this. People that do, materials computational experiments, they can say this Monte Carlo. That's just a type of computer experiment. they can set up different scenarios, and they can say, all right, here's a microstructure. The black and the white might represent two different phases present, and the red line represents what an electron does when you apply a voltage across this thing. The electron wants to move over, but you can see it's changing direction and it's bouncing around. Its net motion is to the right because the electric field must be pointing to the left, right? But it takes a lot of bounces along the way. And then as you change the material, for example, changing temperature or changing the amount of dislocations present or all these things that cause scattering events, you can cause many, many more scattering events, which is going to slow it down. Or you can cause less, and it's going to go faster through the material. So instead of calling it terminal velocity, we call it drift velocity, V sub d. And we can write V sub d is going to be equal to the electron mobility multiplied by the electric field. And you'll remember that that's then just equal to electron mobility multiplied by d potential dx, right? That's the difference in voltage over the separation. This now allows us to come up with a very important expression you're going to use on the homework for sure, which is the electrical conductivity should be equal to the number of carriers, n, that's the number of free electrons per unit volume, multiplied by E, the fundamental charge of those electrons, multiplied by mu E, which is the electron mobility. We could write a similar expression for holes. We could say it's the number of holes you have times the fundamental charge. It's going to be the same since it's the absolute value, but now times the mobility of holes, right? Let's not say equal, but we could also say or, right? It depends on which charge carrier is present, whether it's electrons or holes, and we'll talk more about that soon, okay? And this should make sense. If we want to know what our conductivity is, it should scale with either the number of carriers as well as their terminal velocity as they move through material, their drift velocity, okay? Nearly done. A few more things. Let's briefly talk about electrical resistivity in metals. We know that electrical resistivity in metals is low. They have a large conductivity, low resistivity because you have lots of free electrons, right? We just said that conductivity is equal to the number of electrons times the charge of the electron times their mobility. And there's lots and lots of these in a metal, right? And therefore we expect high conductivity. Nevertheless, we can make a metal more resistive, and the way we do so is by introducing scattering events. Now what's really interesting is the electrical resistivity, we can actually add it up in terms of each constituent that scatters it. So you have some amount of resistivity coming from thermal scattering, some amount of resistivity coming from impurities, from deformation, and so on. This is known as Matthias Ins Rule. So here's pure copper. It has some slope, meaning its resistivity, plotting resistivity here against temperature here. It has some slope, right? And you see that for all these samples going above it, they have roughly the same slope. They're all becoming more resistive with increased temperature. That is due to rho thermal, right? Thermal vibrations, as you warm the thing up, atoms are vibrating more and more. Therefore, electrons are scattering more and more off of these vibrating atoms. However, you can also make it even more resistive as you go from pure copper to copper that has some amount of nickel deformations, impurities, excuse me. Those impurities also serve as scattering sites. Then if you deform the copper, meaning you cold work it and you introduce dislocations or twinning or all these defects in it, that can further increase the resistivity, right, and so forth. Okay? This gives rise to an important concept. The electrical resistivity in metals should increase with temperature. This is a basic definition of metals. If you measure the electrical resistivity and it goes down with temperature, you do not have a metal. You have a semiconductor, right? This is a basic definition, definition, right? Also, you should expect to see resistivity increase as you go from a pure material, pure right here, towards adding impurities. Right? Furthermore, after 50%, at some point we're going to see that it's going to drop down because we'll reach 100% over here, and you have a pure material, so it should also go back down again. Probably not as low as pure copper because copper is a better conductor than nickel. Oh, sorry, this is resistivity. It should go lower. You understand though. A few last things before we end this video right now in about 5 minutes. For metals with electrical conductivity, a few terms to be aware of. If you ever hear people mention oxygen-free high conductivity copper, OFHC copper. That's just copper where they've removed as many impurities like oxygen that, believe it or not, is actually present in it in very small amounts, and that increases the electrical conductivity. Another thought is aluminum. Aluminum has half the conductivity of copper, but copper is about 3 times as expensive as aluminum. So if you're looking at conductivity per cost, aluminum actually wins out. And this is why homes built, I don't know when, maybe before the 50s or so, had aluminum wires in them. However, they found out that that was unsafe because aluminum has a much lower melting point. And so basically there was problems with overheating in the wires. They would melt, that would cause short circuits, some overheating, and eventually fires. So in now modern day homes, they've replaced aluminum wiring in the electrical outlets with copper wiring. Silver is one of the best electrical conductors. If you form solid solutions, you reduce conductivity, but you might increase strength, so it might be necessary. And then I've already mentioned nichrome as a metal that is an important one because it has good conductivity. So that is the video for today, and we will have a brief quiz on this in class on Monday, and we will talk more about that in subsequent videos for this chapter.